Hey everyone, and welcome back to the channel where we demystify the amazing world around us. Today we're diving deep into a phenomenon that sounds a bit like something out of a sci-fi movie. But trust me, it's very real and incredibly important for understanding our planet: soil liquefaction. Now you might be thinking, soil turning into liquid? How does that even happen? Well, get ready. Because we're not just talking about it happening, we're talking about how rapidly it can occur, sometimes in a matter of months. It's a truly fascinating and sometimes frightening geological process. So, let's start with the basics. What exactly is liquefaction? Imagine you're at the beach and you step on some wet sand near the water's edge. You feel your foot sink, and the sand beneath it becomes squishy, almost like a fluid. That's a tiny, harmless example of liquefaction. On a larger, much more dangerous scale, soil liquefaction happens when saturated, loose granular materials like sand or silt temporarily lose strength and stiffness and behave like a liquid rather than a solid. This typically occurs in response to an applied stress, most commonly seismic shaking during an earthquake. It's like shaking a bottle of sand and water. The sand can suspend and flow. To really get our heads around this, we need to understand the composition of soil. Most soils aren't solid blocks. They're made up of individual particles with spaces or pores in between them. When these pores are filled with water, we call the soil saturated. Normally, the weight of the soil particles rests on each other, creating friction and stability. But here's where things get interesting. When an earthquake strikes or even heavy machinery is at work, the ground vibrates intensely. This shaking causes the soil particles to rearrange themselves. They try to settle into a denser configuration, but because the pore spaces are filled with water, that water gets compressed. Now, water is almost incompressible. So, as the particles try to move closer, the pressure of the water in those pores rapidly increases. This is called pore water pressure. If this pore water pressure builds up to the point where it exceeds the pressure holding the soil particles together, the soil literally loses its ability to support weight. It's like the water is pushing the particles apart, reducing the friction between them to almost zero. And just like that, what was once solid ground can transform into a soupy, unstable mess, behaving more like quicksand than solid earth. Structures built on top can sink, tilt, or even topple over. It's a major hazard in earthquake-prone regions. Now, here's the kicker, and what makes this phenomenon even more critical. Rapid liquefaction can occur within months. You might think geological processes take thousands, if not millions of years, but the conditions for liquefaction can develop surprisingly quickly. How? Well, it often comes down to changes in the groundwater table or sudden deposition of new, loose sediments. For instance, consider areas near rivers or coastlines. If there's significant flooding or a sudden rise in the water table due to heavy rains, soil that was previously dry or only partially saturated can become fully saturated in a relatively short period. When that happens, those soils instantly become vulnerable to liquefaction if seismic activity occurs. Another scenario involves rapid sedimentation. Think about deltas or river estuaries where sediments are constantly being deposited. If a large amount of loose, fine-grained sand or silt is laid down quickly, it might not have enough time to compact and consolidate naturally. These fresh, uncompacted deposits, especially if they are saturated by groundwater, are prime candidates for rapid liquefaction. It's like building a sandcastle on dry sand versus building one on very wet, loose sand near the waterline. The wet, loose sand is far more susceptible to collapsing or shifting. One fascinating and sometimes tragic example of this can be seen after major floods. As floodwaters recede, they often leave behind layers of new, unconsolidated sediment. If an earthquake were to strike in the months or even weeks following such an event, these freshly deposited, water-saturated layers could liquefy with devastating consequences. It's a stark reminder that our landscape is constantly evolving, and sometimes those changes can happen at a pace that catches us off guard. The rapid development of liquefaction potential isn't just about natural events either. Human activities can also play a role. For example, some construction projects involve dredging or creating artificial fills, which can introduce large volumes of loose, saturated material. If these new fills aren't properly compacted or drained, they can quickly become highly susceptible to liquefaction. Even changes in irrigation practices in agricultural areas can alter groundwater levels, impacting the saturation of underlying soils and potentially increasing liquefaction risk over a relatively short timeline. Understanding this rapid development is crucial for urban planning and infrastructure design, particularly in earthquake-prone zones. Engineers and geologists have to constantly monitor soil conditions and groundwater levels to assess the current risk. This involves taking soil samples, conducting in situ tests to determine soil density and water content, and modeling how seismic waves might affect different soil layers. Knowing that conditions can change quickly means that these assessments aren't just one-time events, but rather ongoing processes that need to adapt to environmental shifts. So, what can we do about it? Mitigating liquefaction risk primarily involves engineering solutions. One common technique is ground improvement. This can include things like vibro-compaction, where large vibrating probes are used to densify loose sands, or stone columns, which involve drilling holes and filling them with compacted gravel to create drainage paths and reinforce the soil. Another method is drainage, where systems are installed to lower the groundwater table or allow excess pore water pressure to dissipate more quickly during shaking. These methods aim to either make the soil denser, reduce its saturation, or provide an escape route for the high-pressure water, thus preventing it from pushing the soil particles apart. In conclusion, soil liquefaction is a powerful geological process where saturated, loose soils temporarily lose their strength and behave like a liquid, most commonly due to earthquake shaking. The astonishing part is that the conditions for this phenomenon, like increased soil saturation or the deposition of fresh uncompacted sediments, can develop incredibly rapidly, sometimes within just a few months. This makes it a dynamic and continuously evolving hazard that scientists and engineers are constantly working to understand and mitigate. It's a testament to how complex and surprisingly active our planet truly is, even at the microscopic level of soil particles and pore water. Thank you so much for joining me on this journey into the fascinating world of soil liquefaction. I hope you learned something new and found this explanation helpful. If you enjoyed this video, please hit that like button, share it with your friends, and don't forget to subscribe for more intriguing science education content. We love bringing you these insights, and your support helps us keep doing what we do. See you next time.